You are listening to the Vision Learning recording of Introduction to Paleoanthropology, Bones, Stones, and Tools, written by David Warmflash, MD, and Nathan Lentz, PhD. Vision Learning is funded in part through grants from the National Science Foundation and the U.S. Department of Education. Imagine that you're an advanced Boeing 787 and a population of such aircraft that don't know the history of how they came to be, but they figure that they probably evolved from earlier flying machines. Now, suppose that you find remains of aircraft that existed in the past, more primitive, but the remnants are not entire aircraft. They're just pieces. Someone finds blades from the turbine of a jet engine made in the year 1947. Another researcher finds material from an early 19th century hot air balloon. Part of the control panel from the gondola of the 1930s Zeppelin is identified. Excavations have yielded parts of fuel lines, a rudder, and different kinds of nuts and bolts from various extinct planes. Then there's a big find, part of a wing from one side of the 1903 Wright Flyer. Figure 1. First successful flight of the Wright Flyer by the Wright brothers. Can you extract information from such fossils? Enough to show a pattern of changes that reasonably recounts the evolution of powered flight? This may sound puzzling as an opening to a lesson on human ancestry, but it parallels how we've learned most of what we know about human ancestry since the time that our line diverged from that of our cousins, the great apes. A clean progression. Since 1997, scientists have been using sequences of DNA extracted from human bones to study the human lineage, using this information to confirm, refute, or modify what we've learned from the fossil record alone. DNA might be the equivalent to finding the blueprints or the black box from one of the fossilized aircraft. Scientists have even been able to extract DNA from some extinct human species, notably Homo neanderthalensis, Neanderthal man, that existed alongside modern humans. See our module Y chromosome and mitochondrial DNA haplotypes, Tales of Human Ancestry. This has led to some major revelations. But DNA has been recovered only from bones up to about 400,000 years old, and even then, samples are very limited. To reveal the full story of human ancestry that goes back much earlier, scientists still depend on a much older strategy of analyzing fossilized bones and teeth, the stones and sediment in which such bones are buried, and the tools made by the creatures to which the bones once belonged. Scientists who do this are called paleoanthropologists. They have been around since Darwin's era. The first skull to be called H. neanderthalensis was discovered in 1856, 3 years prior to Darwin's publication of On the Origin of Species. That first skull dates back 40,000 years and was found near Dusseldorf, Germany, in the Neander Valley. Because it was the first such skull to be recognized as belonging to a species separate from modern humans, it became the name of the new species. Earlier in the century, 3 other skulls had been discovered, 2 in Belgium and 1 in Gibraltar, that later were recognized as Neanderthal. In On the Origin of Species, Darwin avoided talking about the origins of our own species, but he got bolder 12 years later in The Descent of Man and Selection in Relation to Sex, published in 1871. Humans and apes shared an ancestor, he proposed. The divergence occurred millions of years ago, and today there is no doubt that he was correct. Comparison of human and chimpanzee genomes shows that the 2 lineages split 5 to 7 million years ago. Darwin further suggested that humanity's birthplace had been in Africa, but he left it to the next generation to do the fieldwork and analysis needed to test that hypothesis. While the concept of multiple species was paramount to the new Darwinian paradigm, early visions of the ape-human divergence were not as sophisticated. Similar to the ancestral lines of kings of the reigning European dynasties, Victorian paleoanthropologists hypothesized a single clean progression from a species bearing all ape qualities to a species that was recognizably human. Along that progression, they assumed that brain enlargement led the way in distinguishing humans from apes, with other traits such as upright walking developing later. They were looking for a kind of ape-man fossil. They called it the missing link, and initially they thought Neanderthal, figure 2, might be a good candidate. But the Neanderthal brain was roughly the same size as that of a modern human, so they decided it wasn't the link they wanted. Rather, Early paleoanthropologists hypothesized H. neanderthalensis to be the species that had come just before H. sapiens. This meant they now needed to look for a fossil of a still older group of humans, something that shared some characteristics with Neanderthals, yet also was slightly ape. That was the missing link they had in mind. Figure 2. A model of a Neanderthal, H. neanderthalensis, man. The quest for the missing link. Today, we know that the human family tree is highly branched, and various human-like species have been categorized into a handful of genera. One genus called Australopithecus consists of species, all extinct, that were more ape-like than human, but nevertheless somewhat more human than any ape alive today. The other genus, called Homo, includes modern humans, Homo sapiens, plus various extinct species, including H. neanderthalensis, that appeared more human than ape. Together, Australopithecus, Homo, and two other extinct genera are collectively known as hominins. Similar to our aircraft analogy, the amount of bone that has been discovered from extinct hominid species is scant. Findings are so rare that a professional paleoanthropology field researcher can go through an entire career without ever finding a hominin fossil. At the same time, the discovery of a key fossil has the potential to change major aspects of what is thought about the evolutionary pathway to modern humans. Fossils do not provide us with the precise lineage, species to species. What they do provide is a blurry picture of the evolution of skeletal features and tools, a picture that gets blurrier the further back we look. Despite Darwin's idea of Africa as humanity's birthplace, the presence of H. neanderthalensis in Germany, Belgium, and Gibraltar suggests to late 19th century paleoanthropologists that humans had taken their modern shape in Europe. And if Neanderthals evolved into modern humans in Europe, their reasoning was that a species still more ancient must have evolved into H. neanderthalensis, also in Europe. So immersed were paleoanthropologists in the hypothesis that brain enlargement had led the way in human evolution, and so seduced were they by the prospect of Europe as humanity's birthplace, that they fell into the trap of confirmation bias. They paid attention to evidence that seemed to confirm their ideas, while ignoring evidence to the contrary. As a symptom of this bias, nearly all of the experts overlooked a major finding in the early 1890s. On the Indonesian island of Java, Dutch paleoanthropologist Eugene Du Bois discovered a species that he thought was a human ancestor much more ancient than H. neanderthalensis. There was a femur, the bone that forms the thigh and hip, and a cranium, the latter accommodating a brain size of 940 cc, roughly 2/3 to 3/4 the size of a modern human brain. Ironically, this was exactly what the established paleoanthropologists expected for the long-sought missing link. But many thought that other preserved parts of the skull were too ape-like. Moreover, the specific shape of the knee showed that this extinct creature could lock its knee joint straight. In other words, it was an upright walker, and so it was called Homo erectus. In later decades, fossils of H. erectus would be discovered throughout Asia, Europe, and Africa. It was an immensely successful species that existed from roughly 2 million until roughly 400,000 years ago, far longer than modern humans have been around. Today, it's clear that H. erectus was almost certainly a direct ancestor of our species. Even based on Du Bois' single specimen in the 1890s, which they dubbed Java Man, the species should have been the top candidate for the ancestor of modern humans. Yet, the bulk of Victorian paleoanthropologists downplayed the discovery. It conflicted with the popular notion that humans had developed a full-size brain before they stood up. Nevertheless, because of Java Man, Du Bois and his followers stated a new hypothesis. The birthplace of humanity was not Europe nor Africa, but Asia. A cautionary tale of two skulls. At the turn of the 20th century, Great Britain was one of the two leading centers for human origins research, the other being Germany. Anyone in the English-speaking world who wanted to rise in the field of paleoanthropology would go to England to study with the top experts. One such expert was Sir Grafton Elliot Smith, a pioneer in the utilization of new technology. He was the first to employ X-ray imaging to study Egyptian mummies. Just after World War I, Smith traveled to his native Australia, where he gave a lecture on human origins. In the audience, Raymond Arthur Dart, a student of biology and medicine, was so fascinated that he relocated to London to work with Elliot Smith at University College. There, Dart was thrilled to rise up as a star protege, not only of Elliot Smith, but also of another leading researcher, Sir Arthur Keith. In 1922, both Keith and Elliot Smith pressured Dart to accept a professorship in the new anatomy department at the University of the Witwatersrand in South Africa. 2 years later, workers in a South African town called Taung dug up a strange skull, and pretty soon, Dart got to examine it. Dart could see that the Taung child, figure 3, skull was different from H. erectus. In particular, the cranium was small, not much larger than that of a chimp juvenile. But after 7 weeks of tedious work picking away the rock into which the face was embedded, Dart noticed certain human characteristics in the jaw, teeth, and other areas. Plus, the skull displayed more information. Beak marks in the bone hinted that the ancient child had become prey to an eagle. Figure 3, 3D forensic facial reconstruction of the Taung child. Under the mud of 2.5 million years, the cranium had filled with just the right mixture of sediment and water to act as a kind of paste similar to what dentists use to create a cast of a patient's teeth. Inside the Taung child's skull, the sediments had created what's called an endocast, a model of the exterior surface of the brain. This is something paleoanthropologists who study hominid brains often do intentionally, because the shape of the inside surface of the cranium follows the convolutions of the outside of the cerebral cortex. This in turn can provide useful information on the anatomy of the brain that once occupied the fossilized skull. Dart assigned Taung child the scientific name Australopithecus africanus, meaning Southern Ape of Africa. It was the first Australopithecus species to be identified. In 1925, Dart published his initial findings in a paper in the journal Nature, asserting A. africanus as an ancestor in the line that diverged from that of apes and became human. He didn't use the term missing link, but that's how it was described in popular media. For a couple of weeks, Dart was a celebrity, but the bulk of paleoanthropologists quickly dismissed Taung child. Critics included none other than Dart's former mentor, Sir Arthur Keith, who condescendingly told Dart that he had discovered some new variant gorilla. The British paleoanthropology community would hear nothing of the small brain missing link. This was mostly because a prior find was casting a shadow over Dart's discovery. Back in 1912, an amateur archaeologist named Charles Dawson had presented to the Geological Society of London what looked like a major find. It was a skull that, according to Dawson, workmen had unearthed 4 years earlier in a quarry. The brain size was a little smaller than that of a typical modern human. The jaw was more ape-like, with teeth smaller than those of apes, but not quite as small as human teeth. The discovery took place during the lead-up to World War I, with Great Britain and Germany in massive competition in all possible ways. Science was no exception. With the Neanderthal discovery linked forever to Germany, English fossil hunters longed for an equally important discovery on British soil. Dawson's discovery, figure 4, was just what they wanted, a skull of a human ancestor. Although modern dating techniques had yet to be invented, it seemed much older than any H. neanderthalensis skull and was excavated in a town of Piltdown in England. This part ape human ancestor was an Englishman. Figure 4, Piltdown excavation timeline, including the main events and discoveries. In the 1940s and early 50s, the Piltdown skull was exposed as an elaborate hoax. A sham fossil built from a human cranium, an orangutan jaw, and chimpanzee teeth, filed down to look more human-like. See our module, The Piltdown Hoax, a lesson on confirmation bias in science for more information. But when Dart made his A. africanus discovery in the 1920s, Piltdown man was still the rage in the anthropology community, which preferred the story that this fossil told rather than the reality revealed by the Taung child. Textbooks and university courses dealing with human origins in the 1920s and 30s did not even mention Dart's Taung child skull. Although there was much to learn from the endocast, scientific journals would not accept another paper from Dart. For the bulk of 2 decades, the steady stream of rejections affected him personally and destroyed his motivation. It was not until the 1940s, as more A. africanus skulls and bones were unearthed in Africa, that Australopithecus was really starting to look irrefutable as a genus of pre-humans. Dart was vindicated. Finally, in 1947, Sir Arthur Keith apologized, announcing, "Dart was right and I was wrong." Searching for the toolmaker. By the middle of the 20th century, paleoanthropologists were coming to grips with the prospect that brain enlargement was not the characteristic that had first distinguished human ancestors from apes. But if not the brain, then what feature had set human ancestors on course? Louis Leakey of Kenya thought it had to have been tool making. Going deeper through geologic layers takes one backward through time, not only in terms of biological remains, but also archaeologically. The sediment layers of the Earth can be dated with geological and chemical techniques, and as we move deeper into these sediments, we find tools of decreasing complexity. In the 1950s, Leakey's hypothesis was that the same geologic layer that shows the simplest tools should also show fossil evidence of the tool-making species of that era. He also hypothesized that such a toolmaker should show the beginning of notable brain enlargement and show features of the face and teeth intermediate between A. africanus and H. erectus. In 1959, Leakey's wife, Mary, discovered a fossilized skull of a previously unknown hominid in Tanzania. It was found at the same geologic level as some crude hand axes and other early tools. The skull had a more robust jaw and larger teeth than A. africanus. The Leakeys named it Zinjanthropus boisei, though eventually it was renamed Australopithecus boisei. It is also called Paranthropus boisei, based on the idea that boisei and certain other robust hominid species should be placed in a genus separate from Australopithecines. For Mary and Louis Leakey, the running hypothesis was that A. boisei must be the tool maker. Otherwise, what would the species be doing at the very same site and in the very same geologic layer as the tools? But there was a problem. The specimen had a cranial capacity of just 530 cc. That's slightly larger than the brain of an adult chimpanzee, ranging from about 275 to 500 cc, or A. africanus, 420 to 500 cc, but the same as a typical gorilla. See Figure 5 for the evolution of brain volume in hominini. Apes can use sticks as tools to coax termites out of trees, but this does not require the long-term planning and dexterity needed to flake a rock, turning it into a sharp tool. That's the kind of tools present in this layer, and this seemed beyond what an A. boisei brain was capable of crafting. Figure 5, the evolution of brain volumes in cc for different hominini. The very next year, the Leakeys discovered another hominid skull at the same location and the same geologic layer as the tools and the A. boisei specimen. Over the next few years, it became clear that this was a fossil of a different hominid species. Because the skull was in pieces, with parts missing, it was not possible to obtain a precise cranial capacity, but rather a range. That range was estimated at 590 to 710 cc. Clearly larger than any Australopithecine brain, but smaller than that of H. erectus. That must have been the toolmaker, and the Leakeys called it Homo habilis, meaning handyman, assigning it to the same genus as modern humans based on the idea that toolmaking is what set the genus apart from Australopithecus. The finding also meant that two hominid species had existed at the same time and place. That was interesting, given that several small-brain hominid species had been discovered by this point. Not just A. africanus and A. boisei, but also another called Australopithecus robustus. Clearly, a clean linear progression from apes to modern humans was not going to hold up. Instead, the emerging fossil record told a story of a human family tree with many branches, filling in details and posing new questions. Toolmaking was one feature that made human ancestors very different from those of apes, but it was not the only feature. Getting a handle on other features would require more bones, but most of the Australopithecine finds through the mid-20th century were parts of skulls, or sometimes also very small pieces of other body parts. In a concerted effort to find more hominid bones, teams of scientists began exploring the Afar Triangle region of Ethiopia, near the Hadar village, where the geology and climate had been ideal for preserving and burying skeletons. Camps were set up in the early 1970s, and prominent scientists were invited to visit. These included Mary Leakey and the rising star in the paleoanthropology community, Donald Johanson of the Cleveland Museum. Johanson and other team members in 1974 unearthed what is now the most famous hominid skeleton. Although incomplete, virtually everything that is missing on one side of the body is present on the opposite side. The bones of this skeleton matched previously discovered specimens of the species Australopithecus afarensis, but they also showed something new. Examining the knee joint, Johanson and his colleagues saw that it could lock the leg into a straight position, just like that of the legs of H. erectus and modern humans. Furthermore, the location of the foramen magnum, the hole at the base of the skull, was well defined in this specimen. These two features meant that A. afarensis walked upright rather than skimming along on its knuckles like an ape. But just like A. africanus, the brain volume of A. afarensis was only chimpanzee size. Furthermore, this species was more than 1 million years older than H. erectus. Figure 6 shows the 3 species skulls. Figure 6. 3 models of skulls, A. africanus left, A. boisei center, H. erectus right. Johanson's team named the specimen Lucy because they were listening to the Beatles song Lucy in the Sky with Diamonds while examining their find. Because its jaw was less massive compared with other Australopithecines, A. afarensis is thought to be either a direct ancestor of the human line or at least closely related to such an ancestor. In contrast, A. africanus, A. boisei, and A. robustus are now recognized as offshoot branches of the line that leads to Homo. This fits with the Leakey finding of A. africanus coexisting with H. habilis. They were cousins whose progeny were destined for very different fates. Questions of taxonomy. It's clear that the Australopithecus genus gave rise to Homo, but every discovery in every fossil raises further questions. When it comes to the placement of species into a genus, for instance, what is appropriate? Nobody would argue that H. erectus is miscategorized in the Homo genus, but the Homo genus is probably the most poorly defined genus of all taxonomy. Leakey's attempt to use a behavior, toolmaking, to define the genus is problematic because we can't always know what a species did or didn't do. We don't always have fossilized tools available. Can we use brain size to define Homo? H. habilis skulls excavated since Leakey's initial find support an estimated cranial capacity of roughly 640 cc on average for the species. That's in the middle of a range starting just below 600 and going just beyond 700 cc. It's intermediate between the Australopithecine and H. erectus. A species called Homo ergaster, hypothesized to be the ancestor of H. erectus, boasts a cranial capacity overlapping with H. habilis and averaging only slightly higher. That suggests a smooth transition between H. habilis and larger-brained Homo species, supporting membership of habilis in the genus Homo. Even if a genera can be distinguished, assignment of species status can come into question when considering excavated specimens. The rationale is solid that H. erectus is a distinct species from H. habilis and from modern humans and Neanderthals. But H. ergaster is intermediate between H. habilis and H. erectus. Similarly, there's Homo heidelbergensis, which may be descended from H. erectus and the common ancestor of modern humans and Neanderthals. The more specimens that are unearthed and found to be an intermediate form of a known species, the less confident we can be about two groups being separate species. It is important to remember that evolution is a gradual process. Animals live, breed, and die, oblivious to our attempts to name and classify them. Life is never as neat as we'd like it to be. As the ability to retrieve and utilize DNA from trace and ancient samples continues to improve, we gain new tools to answer these difficult questions about how the human family tree is constructed.